Today I'll be talking about acids and bases. So the first thing I want you to do is just take a minute and try and think about what your definition of acids or bases are. Most of us have some experience with the words acid and base, or we have some experiences where we know that some things are acids and some things are bases. And I just want you to take a minute to reflect and think about what you think that the word acid means and what the word base means. So maybe pause the video and think about it for a second, write some things down, and then hit play again. I've got a couple different definitions of an acid right here. So one is that it is a proton donor. And here, what we mean by proton is essentially what we're talking about is an H plus atom. And the deal is hydrogen only has one proton because it's atomic number 1. And then it has 1 electron if it's neutral hydrogen. And then it has 0 neutrons because the most common form of hydrogen has a mass of 1. If you look it up on the periodic table, you'll see that the molecular weight of hydrogen that's listed there is 1.01. And so that means that the most common isotope of hydrogen is hydrogen 1. That means it just has its proton, no neutrons. And so if we've got something that's a proton and an electron, this is the hydrogen atom, and then it loses that electron, it becomes H plus, and all that's left is the proton. And so when we say proton donor, we mean really like a positively charged hydrogen nucleus. And that just is one proton. It's sort of synonymous, actually. A singular proton and a hydrogen plus atom are the same thing. And so that's one definition of an acid, something that will give up these hydrogens, these H pluses. Another definition is that it's an electron acceptor, which is sort of the opposite of a proton donor. Base is defined the opposite way. So bases, they will give away electrons, they'll take in protons or take in those H pluses, and that's sort of the scientific definition that we go with for this. There are other definitions actually out there too. There are something like 3 or 4 different definitions for acids depending on different criteria, and so these are the ones though that we're going to go through as the basic ones. Listed here, you can see some different characteristics of acids. So if you get it on your skin, it'll start to sting and burn after a little while. If you put litmus paper, that's that paper that you dip it inside and it changes colors, it's going to turn it red if it's an acid. If you've got a base and you add an acid to it, it's going to cancel out that base or neutralize the base. We say it's a proton donor, so there's that H plus donor. And then on the pH scale, which I'll talk about more in just a minute, we say it's less than 7. And things that tend to be acidic tend to taste sour. So if you think of like citrus fruits or like warhead candies or things like that, those have acids in them. That's what makes them taste sour. Bases here, these are the characteristics for bases. If you get it on your skin, you'll notice that it starts to feel slippery. And so what's happening there is the oils in your hands are being converted into sort of like a soap. And so what happens is your hands get all slippery and you're like thinking, hey, I didn't put my hands in any soap, like why are my hands slippery? And then it's going to start to actually burn a little bit after that as well. So it's not like you wouldn't feel any pain if you had a strong base on your hands. It just, the first thing you feel is a slippery feeling, and then it starts to hurt after that. If you put litmus paper in a base, it's going to turn blue. If you mix it with acids, it cancels out or neutralizes that acid. It accepts protons, those H pluses. And I'll talk about that more again when I talk about sort of acid-base reactions and how that works. If you taste something that has a base, it's going to taste bitter. Like if you've ever had coffee or tea that's overcooked or oversteeped, it tastes really bitter. And then on the pH scale, we're talking about things that are larger than 7. All right, so there's a question here about acids and bases and which one here is more dangerous. Many of you have seen some acids do some pretty dramatic things, and so there are a lot of videos and cultural references to acids being really dangerous, and so that tends to make people think that bases aren't as dangerous. In reality, bases are actually just as dangerous as acids are. I have a video that I played in class about a guy who drank some industrial cleaners and he found out, bases very, very dangerous. They do really bad things just as well as acids. And so to try and kind of help you remember, both of them have the ability to melt your face off. It says here, really, I mean, what it's saying is both of them can really, really hurt you. It's not really that one of them is more dangerous than the other. They're just, if they're highly concentrated, both very, very dangerous. So stay clear of things that are strong acids or strong bases. Here we've got the pH scale. On the left side, we have the acidic side. The strongest acids are listed there under the pH of 1. And so hydrochloric acid, nitric acid, sulfuric acid, those are really, really strong acids. We've got a weak acid listed in the middle here, ethanoic acid. What weak acid means is that like it gives away some of its protons, but not all of them. In the middle, like distilled water, we have 7 for our pH. Ammonia is kind of a weak base. It accepts some H pluses, becomes ammonium. It becomes the ammonium ion, but it won't accept, tons and tons of those H's. Sodium hydroxide here, that's the strongest base. And so this one here is an OH. It has an OH on it. It's NaOH. And things that donate OHs are really, really good at taking in hydrogens because H plus mixes really well with OH minus to make water. So sodium hydroxide, very strong base there. All right, so the term pH, I think that you've heard a whole lot probably in your life in reference to acids, and the problem with that is you don't really know what it means, and so that P on the pH is actually just a mathematical operator, and it means negative log of something. And so other mathematical operators that you have would be like times divided by the caret symbol, those are all mathematical operators. The P just means take the negative log of what comes after it. So pH means take the negative log of the concentration of H. POH means take the negative log of the concentration of OH. If we had P of the volume, it would mean take the negative log of the volume. So the P just says negative log. Again, talking about what the pH scale means, a lot of you are familiar with this, but going less than 7, we're acidic, more than 7, we're basic, equal to 7 is neutral. Something that you might not know is that for every increase in 1 on the pH scale, we have a multiple of 10. So what I'm saying here is that if we're talking about concentrations of hydrogen, H pluses, inside of an acidic solution, if we're talking about the difference between like a 4 and a 5, 4 is more acidic than 5 is, okay, because it's lower on the scale. It's more acidic if it's lower on the scale. So 4 is more acidic than 5. And because it's 1 away, it's going to be 10 times as acidic, meaning it's going to have 10 times the H plus atoms in there. If you had 4 and 6 and you're comparing those, 4 again is going to be more acidic, but now it's 2 steps away, which means 4 is going to be 100 times as acidic. If you're looking at the difference between 6 and 1, that's 5 away. So a pH of 1 means that it's 100,000 times as acidic. And so those sorts of things, something to keep in mind so that you can interpret what the different pH values mean. So this gives you an example here. Yeah, 10,000 times if we're comparing a pH of 1 and a pH of 5. The difference there is 4. So kind of a trick here. If you have a difference, just however many the difference is, that's how many zeros you have here. So 1 is more acidic than 5. The difference is 4, so it's going to have 4 zeros, okay, because it's 10 to the 4th power, or 10,000. That's the difference there. So later on we're going to be talking about this value, this 10 to the negative 14th, which actually comes up a lot in this unit. Where that 10 to the negative 14th comes from is it's actually an equilibrium constant. If you remember back to the last unit, you do products over reactants, but you don't include solids or liquids. So if we do the products, we get H plus times OH minus. They're both to the 1st power because they have coefficients of 1, so you can see that. And then the liquid is left out because it's a liquid. So this is the entire equilibrium equation here, H plus times OH minus. And it's a really, really small number. And so thinking hard back to the last unit, if we've got an equilibrium constant that's really, really small, it means that it is reactant favored. And so when we have water, it goes through this autoionization process, which means that it's breaking itself apart into the H plus and the OH minus, but it's so reactant favored that it's almost entirely water when it's at equilibrium. However, this does create a relationship between the amount of H pluses and OH minuses that you have in a solution because of that equilibrium that exists. The last thing I'm going to talk about here is some different terminology in terms of the number of hydrogens that are available to donate. So some acids actually can donate multiple protons. Some of them only have 1 proton or 1 hydrogen to donate. So When we say monoprotic acid, that term means that it just has one hydrogen. You can see HCl, which is hydrochloric acid, or NO3, which is nitric acid. Those ones just have one hydrogen available. However, if you go to something here like the sulfuric acid, it's got two hydrogens available, so that makes it diprotic. And then we even get triprotic acids like this H3PO4 or phosphoric acid that has three different hydrogens that it can donate. Something to mention with this, if it's already donated one hydrogen, it's harder for it to donate the second one, and even harder for it to donate the third one. So a lot of times there are equilibriums in here where it's donated just one or just two of its hydrogens without donating that third one. So that's how that works. So I'm expecting you to know that terminology there.